Right, so continuing on to chapter 8, the moon and Mercury. Finish that today. We might actually start to get into chapter 9 on Venus a little bit. All right, so again, I'd like to show this just because it compares Mercury with some of the larger moons in the solar system. Somebody asked me after class on Tuesday if Mercury should be considered a planet since it's actually smaller than the sun and moon. That's a fair point, but the thing is that the size of the body relative to a moon actually is just not part of the technical definition of a planet that's adopted by the American Astronomical Union. So Mercury is certainly large enough and rocky enough. You might say it's massive enough to be a planet, even though it's actually smaller than Ganymede, which is one of the moons of Jupiter. It's actually more massive than Ganymede, because Ganymede in the outer solar system turns out to be a very icy composition. So if you think of it in terms of mass, you could still say that even though Mercury is a little bit smaller in radius, it's actually still a more massive object. And so this is actually a pretty old photo of Mercury, and this is one of these newer ones that the Mercury Messenger has produced. And we're going to be talking a little about today about a feature down here that you can't see too well in this particular view, called the Calorus Basin, which is the site of an ancient, huge impact on Mercury that's had profound consequences for Mercury's spin. Surprisingly enough, as we'll see. Okay, so just to quickly review a few things that we went over already. The average density of the moon is the total mass of the moon divided by the total volume. And when we do this, we get 3.5. So that's surprisingly low, you might say. I mean, it's not as high as any of the terrestrial planets. It's about similar to the density of Mars, but it's a lot lower than the density of the Earth. But right away, just from this one number, we can conclude that the moon does not contain very much iron. It's got to have a rather different composition from the Earth. Surface gravity on the moon, again, it always looks kind of messy, but it's actually pretty straightforward. This is, of course, Newton's law of gravitation, and then we combine that with Newton's law of motion, F equals ma. And the reason that we're doing this is because F equals ma will tell you what the acceleration A is of a body with mass m if it's hit with that force F. So any force that I give you, if you know the mass of the body, this will allow you to calculate the acceleration in response to that force. Okay? And then we couple that with Newton's law of gravity, which is just actually telling us what the gravitational force is. So remember, this F could be any force. It could be the force of a spring. It could be the force of anything you can think of. But in this case, it happens to be gravity. So that's why we end up with this relationship here. We have two things that F is equal to. It's equal to Newton's law of gravity, and it's also equal to mass times acceleration. Now, this little m would be the mass of your body, let's say. And you see it appears on both sides of the formula, so the little m cancels out, and what we get is this nifty result. Very, very important, because it doesn't depend on the mass of the smaller object, namely, let's say, your body here on the moon. This acceleration is completely independent of your mass. It only depends on the gravitational constant, the mass of the moon here, or the mass of the Earth, or the mass of whatever object we're talking about. And then, of course, the distance that you are from the center of the object. So we just keep applying this over and over again. And when we talk about planets, we're always going to stick in the mass of the planet there and its actual radius, you know, if you're standing on the surface here, at the radial distance from the center. So we just keep applying this for different masses and radii. And so when we do this for the moon, these are the numbers that we have for the moon. We get a surface acceleration of 1.7 meters per second squared. So that means if you drop something, every second after you let go of the object, its speed downward will increase by 1.7 meters per second. Right? That's 1.7 meters per second of acceleration, compared to 9.8 meters per second on the Earth. So obviously this is quite a bit lower. It's 1/6 as large as the acceleration near the surface of the Earth. Now, if we do the same thing for Mercury, this is new, we haven't done this yet, but talking about Mercury, we take Mercury's mass and its volume. And by the way, this is already kind of interesting, because when we look at Mercury through a telescope, we can tell what Mercury's radius is. That's no problem, because we can see the angular size of Mercury through a telescope. We know how far away Mercury is, so because we know how far away it is and its angular size, we can deduce its physical radius or diameter. That's no problem. But Mercury has no moons of its own, so we have no idea about the mass of Mercury at all until we send a spacecraft there, which wasn't until the mid-1970s. Around 1974 is when we first got a number for Mercury's mass. And without that mass, you can't do this simple calculation to get the mean density. So, not until the mid-1970s did we even know what the density of Mercury was. And again, that's the most important single number for a planet, is its density, because that's right away going to tell you, does it have an iron core, for instance? Or is it mostly lightweight silicate rocks? Now in this case, we do get a density that's very comparable to Earth's density, just a teeny bit lower than Earth's density, 5.4 grams per cubic centimeter. So we look at this and we say, okay, this object probably is pretty similar in terms of composition to the Earth. Probably a lot of iron. This number being as high as it is tells us there's a lot of iron. It actually doesn't tell us where the iron is. We really don't know just from that number if there's an iron core or if the iron is somehow distributed through the body. Because we don't know, because you can distribute the iron through the body and you're still going to have the same average density. So this number just tells us there's a lot of iron. But, it tells us this body probably is similar in composition to the Earth. Now, whether or not it has an iron core is actually, I do say that it does have a core here, but that's a little bit further of a leap. And the idea there is because Mercury is so close to the Sun, we presume it probably was completely molten early in its history, and so this dense stuff was able to settle to the core in this process we call differentiation. So, if it's molten long enough, you're going to get the iron accumulating in the core, just as we did on Earth. So, because it's close to the Sun, we think it has a large iron core. And again, just to throw one slight additional comparison, since this is our comparative planetology section of the course. Just thinking about Mars for a moment, Mars is a larger planet than Mercury, but it turns out that Mars is not fully differentiated. The iron in Mars is scattered all over the planet. So again, if we put Mercury out where Mars is, it wouldn't have this iron core. The iron would just be distributed around because Mercury would have cooled off too quickly, just like Mars cooled off quickly because it's so far out from the Sun. So you can see, even though Mercury and Mars are both dwarf planets compared to the Earth, their composition and their amount of differentiation depends on where they are in the solar system. Mercury being close to the Sun, differentiated completely. So again, just the standard comparison. So we think about Mercury, it's closer to the mass of the density of the Earth, and the density of the Moon is closer to the density of the surface rock. So keep in mind again that because the Moon's density is low, not only does it not have an iron core, it doesn't have much iron at all. Because if the Moon had much iron at all, we'd be getting a higher density figure. Okay, so we know for sure the Moon does not have too much iron. All right, going back to the surface acceleration. So the surface of Mercury, gravitational acceleration is 3.7 meters per second squared, which is about 40% of Earth's gravitational acceleration. So objects, if we actually weighed ourselves on Mercury versus the Earth, we weigh about 1/3 or about 40% of the weight that we have on Earth. Okay, so this is just comparing the Moon, the Earth, and Mercury. So we see, this interesting variation. We're not going to see numbers that are larger than Earth's surface gravity until we get to the giant planets like Jupiter and Saturn, because there are no terrestrials with surface accelerations larger than the Earth's surface acceleration. All right, so the ratios here are interesting. The acceleration on the Moon compared to the Earth is 1 to 6. So keep in mind that actually directly implies that your weight is 1/6 of your weight, because remember that the ratio of the accelerations is going to be also the ratio of the weights, because we go back to the F equals ma idea. It's a question of how much force that you're exerting on a spring scale. We take our trusty spring scale with us. Spring scales act the same everywhere because the spring is just a mechanical device. It's going to act the same on the Moon as it does on Earth. But if we go back to F equals ma, what the spring scale is actually measuring is the force that you're squishing that spring with. That's what makes the needle move, right? So remember that F equals ma, the ratio of the A's, the accelerations, is going to be the same as the ratio of the F's, because your mass is the same, unless you went on a diet before you took the moon. I mean, so assume your mass is the same. So the force ratio is also going to be 1 to 6, or 1 to 3 if we compare Mercury with the Earth instead of the moon with the Earth. All right, so just a little summary of some of the key properties here. When we look at the mass of the moon, it's only 1/80th the mass of the Earth. The mass of Mercury is 1/20th mass of the Earth, so Mercury is pretty small. Radii, Mercury is about 40% of Earth's radius, and the moon is 25%. Now, again, if we think about Mars, Mars is about half of Earth's radius. So we usually think of Mercury as being a lot smaller than Mars, but it really is just about 10% smaller than Mars. Mars is really a small planet. It's just a little bit bigger than Mercury. And if we look at the densities, here's where we see another significant difference. The moon's density is only about 60% of Earth's density because of that lack of iron. Mercury is a near twin to Earth's density. So we conclude that Mercury contains a lot of iron, but the moon doesn't. And because Mercury is close to the sun, it's probably highly differentiated. That's the dense stuff sinking to the center. And so we conclude that Mercury's interior is probably similar to the Earth's with a very significant iron core. Now, when we look at these diagrams, we have to always take things like this with a grain of salt because we don't have a whole lot of direct evidence even about the Earth's interior structure. Even the Earth's interior structure is strictly deduced from seismic waves. You know, we can't travel down there, can't send any instrumentation down there into the Earth. But, you know, if you think about it, we don't really understand the Earth's interior too well. Now map that onto Mercury and the moon. These are just wild guesses, basically, right? In the case of the moon, we do have a few small seismic rest that were left by Apollo astronauts, which have measured seismic waves that were created by asteroid impacts. So we kind of know there's a little, you know, probably almost completely solid core in the dead center, but not much there. In the case of Mercury, we've never landed a spaceship on Mercury, nor have the Soviets ever, or the Russians for that matter, anybody. Nobody's ever landed a spacecraft on Mercury, so we don't have any seismometers on Mercury at all. So this structure we're looking at is really just based on two things. One, the mean density that we just talked about, and two, there are observations of the magnetic field of Mercury, which is presumably generated in the molten core, just like it is on Earth. So that magnetic field data gives us some additional information, but you still have to look at these two images here and just realize that they're just, you know, kind of well-educated guesses. But Mercury certainly has a much larger core than the Earth, than the moon's core. No doubt about that. All right, so we've talked a little bit about types of lunar terrain, so we're going to kind of revisit this and talk about kind of analogous terrain that we see on Mercury. When we look at the near side, which is the side we spend most of our time studying, because this is the side we can see from Earth, we see the brighter regions and the darker regions. And it turns out that the lighter regions, which were called Terra in ancient terms, actually turn out to be highlands. They're actually a few kilometers above the darker regions, which are maria, or oceans, seas. Once thought to actually be seas of water. Now we know, of course, they're just completely solid, but they were at one time seas of hot molten material. So in some funny way, the term maria is still kind of appropriate there because they were molten during a period of time after which the highlands had already solidified. And as we're going to see, that, you know, what I just said implies that the maria are younger than the highlands, the Terra, right? If these were molten when the highlands had already solidified, then obviously this is a younger surface. So one of the implications of that is that we would expect, dating lunar terrain. And my little people attempt dating lunar terrain. Anyway,